Okay, I think we can start. I'm slowly going to be going through the registration list and making people contributors. I have posted the link in the chat. If there's anyone here who hasn't registered on Luma and would be like to be made a contributor, please follow that link and register with your full name and surname. So to kind of kick off intros, hello everyone, and thank you all so much for joining us today, this Wednesday. Today we have a session that is being run by one of our partners, Graham. He joined us, I want to say it was I hope it wasn't a month ago, but I think it might have been, for one of our discussions on ontologies and ecosystem code. And from that session, we realized that there's a lot more to unpack and a lot more to share. And so he is leading our discussion today, and he will be presenting a whole bunch of information on ontologies, why we need them, what they are, how we create them, and how we can use them. For some housekeeping, I do just want to say that the session is being recorded and it will be posted to our YouTube channel. With that said, I'm going to hand over to Graham. Thank you.
Okay, cool. Thanks, Maddie. Okay, welcome everyone. I'm going to get straight into it. We've got a lot to cover, and we're already a little bit into the hour, so I'm going to go ahead. All right, so the theme is about taking LLMs, which we know are great and they're useful and they're fun to talk to, but they're not entirely reliable. So we found out after a while that we need to give them context to help them understand our world, to give them better input, to help them work longer without going off track. And that was all good, but we're now into the kind of third stage of this journey, and that is trying to endow them with a little bit of understanding and meaning. And that takes quite a lot more information, and information in a much more structured format. So that's what we're talking about today, is getting to the level where we can have autonomous action by agents, that we can actually trust what they do, and that we can start to deploy this at scale. Okay, so the session is titled Educating AI. And it's kind of like, why I chose that is kind of like you've got this very bright intern that you've hired, and they can do all sorts of things, but you've got to give them some guidance. So you give them operating procedures, you give them your rules for your business, you give them your values that you would like them to follow. And when they go wrong, you beat them about the head a little bit and you guide them some more. And then over time, you train them, you educate them to work the way that you want to work. And that's kind of what we want to do with AI at this point. So we want to stop them hallucinating, we want to get them to give us reliable results, and we want to do it at scale. Okay, so what we're covering today is what is ontology. It's kind of one of those mythical grootwoorde that not everybody knows what it means, why we need it, if we need it, how do we create it, how do we use ontologies, what's happening in the broader industry, and some of the perils of what's happening and how we avoid those, and then a little bit on what we've been up to at Inspired. Okay, so what is ontology? It comes from originally the Greek, Aristotle, sort of the study of the nature of being, onto being, and logos, study of. So it started out in philosophy, really deep stuff. What is reality? How do we describe reality? What is real, etc.? And how do we interact with it and understand it? So it's really there to describe what reality is, and also maybe what we conceive mentally. So things that may not be real as in touchable, physical, but that are real to us. Okay. Now, in recent years, it's become a much more focused topic within information systems and computer science. And a quick way to sort of define it is to say it's a description or definition of concepts, relationships, properties that describe them, that's both concepts and relationships, and constraints and logic of how we use them within a domain. And a domain being like an industry, like retail or telecoms or healthcare, or an area of interest like education or let's say maybe a non-profit or something like that. And then we say, but if we're talking concepts, relationships, properties, isn't that just a data model? And haven't we been doing data modeling for 30, 40 years? And the answer is yes, it is a data model, but not just. It goes a bit further. Okay, so we're going to look at what's different and why it's going further. So what is an ontology? First of all, it is a definition of types of things. So entities, if you like, objects, domain concepts, things like customer, product, vehicle, etc. Its definition of relationships, so subtypes, like teacher is a kind of person, laptop is a kind of product, and so on. Containment, things like a car is made up of components, like an engine, seats, steering wheel, etc. And association, things like customer X buys product Y. Okay. Also roles, so something like a single person might have roles of being an instructor, as well as being a student, as well as being an account holder. Okay. Then we need properties to describe those things. So we might have name, address, balance, image, etc. to describe a person. Also a definition of the data types that we use for these properties. So do we agree what kind of data it is and how we hold that data? So is it a string? Is it a decimal value? Is it a date? Is it some kind of scanned image? We also need constraints around both the data values, validation, relationships, etc., and logic and inferencing. So we want things like, how do we know that the values in a property are valid? How do we know that the relationship is valid? Are some things required? For example, you must have a value for that property, or you must have a particular kind of relationship. For example, you could only capture an order if you have a customer who is approved. In other words, we know who they are, they've got a credit rating, and they haven't been bad. Okay. We also want to know how to derive things. For example, a date of birth doesn't give us an age, but we can calculate an age from a date of birth. So we might want to encode that kind of information, and we might want inference. So if I know that John has a parent, Mark, and Mark has a parent, Fred, then Fred is the first one's grandfather. Okay, so we can infer things from relationships and from other data. Okay, so why do we need it? Well, we need it for competent models. A lot of data modeling in the past has just been, let's put it this way, sometimes more of an art than a science. Okay, it's been a little bit loose, not that rigorous, and maybe only really worked within one organization or within one system. As we, computerize more and more and more of what we're doing in the world, as we interconnect with other parties more and more, and as we go global in scale, we have to have better models that are better thought through, better defined, more rigorous. They have to be shared so that we agree what we mean by them. They have to be rigorous and formal so that they are well structured. And very importantly, they need to be machine processable. So they mustn't be in some document, in some sort of verbose human format. They need to be in a form that is machine processable. Just a very simple example. If you take something like address and you look at this, and here I should probably go into present mode because I have some builds here, so I'm avoiding them. All right, so here is something very simple. We all know how we define an address. Yes, it's first line, last, second line, third line, postal code, country. Yeah. Except when you get to places like Japan, where you will find that they don't have such a thing as street names. The street is seen as the gap between two blocks. So the street name is effectively block 30 and block 31, the thing between. And things like that. And you find addresses worldwide have all these weird characteristics. And if you define an address for one country, as we typically do, it might work for your country. But then you get into Switzerland and you find they have cantons. And you get to Japan and you find they don't have street names, etc. So, you really have to have something that works globally if you're going to set up an international system. Yeah. So That's a simple example of why we need these more rigorous kinds of definitions. And then we may want to not have an address for every country that's different. We want to abstract it up and have a more generic kind of model that will cater for any kind of address. Okay. All right. Then this is kind of what we get if we don't have ontologies. We're asking the friendly agent over here to construct us a useful robot, and the agent doesn't really understand anything. All it knows is probability. All right, it's had its training data and it knows what occurs close to what other things, and it goes and scratches in that pile of stuff and it says, okay, I think this is what you want. Here you go. Here's your robot. Okay. But if we can give that robot something much more structured, like a parts bin that's got all the bits that we need and they're nicely sorted, they're not just in a big heap here, and they're nicely labeled and they're put into categories, then we can get a much better result. Yeah. So this is kind of what we're after at the end of the day. Okay. So how do we build one? The answer is incrementally, iteratively, can be top-down or bottom-up. Very often we want to start with some existing ontology. We don't want to start from scratch because there's already a lot of thought has been put into this and a lot of value is available in existing ontologies. So we want to find the right ones that we can derive from, merge and rationalize. Where necessary, we'll add our own concepts to that. We'll build hierarchies of concepts using specialization and generalization, subtyping, much like we would do in object or entity modeling. We'll relate the concepts together using semantic relationships, and they have particular kinds of relationships, things like containment, association, role. We'll add properties to the concepts to describe them, record their attributes, and we'll type those using the provided data types. We can have properties for relationships, things like when somebody enrolls on a course, that's a relationship, but there could be properties for the relationship itself. When did they enroll? Did they pay a fee? How much did they pay? What did they score on the course? And so on. Then we can add constraints, and this is where we start to get into things beyond data modeling, where we can add these constraints around properties, constraints on relationships, constraints or derivation, rules, and other logic. And then, because we've got well-structured models, we can validate them by running proving utilities, proving algorithms over the ontology to check that it actually is valid. We can populate it with instances, we can navigate it and try typical scenarios and queries. We then iterate till we get that right, and then we can export or share it. Now, when we start looking around, there are a variety of ontologies available to us, and they kind of stratified. So you get upper level or foundation ontologies, and these are very abstract. They're small, they don't have a huge number of concepts, but they are very abstract, but they are very carefully and very well defined. So one of the core ones there is Basic Formal Ontology, BFO, and that is actually an ISO standard fairly recently. And that has very abstract things in it like continuance and occurrence and independent continuance and things like that, that you wouldn't, trip over in your everyday life. But they help us to define lower level concepts much more rigorously. So they will help us to stop defining an event that looks like a person or an account that looks like a person, things like that. Okay, then based on BFO, there are many mid-level ontologies which use a set of common concepts called CCO core, Common Core Ontologies. And these start to get down to real things like a physical object or a human or a product or things like that. Then below those, you'll find domain ontologies that apply in particular disciplines or industries. So you'll find one for space and aeronautics. You'll find one for telecommunications. You'll find another one for retail, and so on. These upper and mid-level ontologies also define a variety of relationship types. As we mentioned, things like subtyping, containment, roles, etc. And they also define a variety of data types for all the commonly found data. For example, dates and addresses and so forth. Okay, some particular domain ontologies derive directly from BFO, not from CCO core. And in there, you'll find many that are particularly the life sciences ones for things like biology and healthcare and diagnostics and so forth. As we go up, these things are more abstract, and as you go down, they become more and more detailed. And the scope varies. This is quite narrow. This gets quite broad. These tend to be for a specific domain or industry, and these go very, very deep into a particular discipline. Okay. Now, also, these ontologies are defined as semantic models and graphs. They're not relational. They're not object models. So, you know, we're familiar with the old relational model, tables, keys, foreign keys, things like that. But it only really works for fairly simple data, debit, credit, balance kind of stuff. The wheels start to come off when you start to model things which are more subtle and or more complicated. Okay. Then we've had an era where the dominant model was really object modeling, and that was good for about 20 years, and that allowed some more subtlety with subtyping and containment and more rich data types and so forth. But again, the limits of that are starting to show. And then the semantic modeling has been around for probably 30 years, but nobody was very interested, except academics, until fairly recently. And fairly recently, the interest has been generated by the advent of AI and us wanting to automate more and more. And then we suddenly discovered that agents don't understand what they're working with. How can we give them more information to reason better? And the answer came in the form of ontologies. So suddenly everybody's interested in ontologies. Now, what is an ontology when we look at it in that sense? It's related to a knowledge graph, and a knowledge graph is very simple. It just has objects or things, relationships between them, and we have things like Joe takes a course which is offered by an institution and so on. And if you abstract up and define the schema or the structure, the shape of what kinds of things you can have and how they can relate, that gives you the basis of an ontology as a graph. So we'll say person is a concept we want to work with, takes is a relationship, course is another concept offered by institution, and so on. Okay, so at its simplest form, it's a very straightforward schema of the knowledge graph. Then there are some languages developed to help us define and describe ontologies. The sort of base one is a thing called Resource Definition Language or Resource Definition Facility, RDF. And that has a very simple form. It has a predicate, subject, object. So we have things like Peter, surname, Jones. So this is a subject. It says we're talking about this object. It has a predicate or something that it refers to it, and it has a value in this case of Jones. Or we can say Peter takes Logic 101, in which case this is a relationship and this is another object that we are talking about here. So it's extremely simple. We call these things triples because they've got three parts. So subject, predicate, object, and very, very simple. But sometimes we want to have this constrained typing or be able to specify the shape of these things without the actual objects or instances. So then we want to add schema. So RDFS adds the schema. And here we're saying we've defined some prefixes which describe where these definitions are held. So that's this little preamble here. I won't go into those. But then we can say things like a person is a class. So in other words, we're now defining a type of thing, not a thing. And we say employee is a class, which is a subclass of person. So now this is giving us the subtyping. And then we can say the properties have a domain and a range, and we have a birthday, which is a RDF property, and its domain is person, and its range is date. So this is saying where this property belongs and what kind of value it can hold. But that still doesn't give us everything we might want. So there's another language that lives on top of that called OWL, the Web Ontology language. All of these, by the way, are W3C World Wide Web Consortium standards. So OWL adds more advanced relationships and constraints, things like we can say a staff member is a class and is equivalent to the class of employee. So what we're saying there is that you can use the name employee or you can use the name staff member. We don't care. It actually translates or means the same thing. Okay, so here we're starting to see more advanced kinds of relationships and constraints. So just to put that in perspective for you, I won't go through this in detail, but we'll share these slides or you'll be able to see the video. So RDF lets you define those triples. It specifies how we identify something, and that uses a global identity based on the web standard, the IRI, your resource identifier. It lets us define literals and data types, blank nodes, which don't have to be visible elsewhere, and graphics, graphs of linked facts. Then S, the schema, lets us define the classes and properties, the subclasses, the domains and ranges and labels. And then OWL builds on those two to let us put in restrictions and cardinality, things like an order can only have one customer, but a customer can have many orders. Equivalence and disjointedness, as we saw, that an employee and a staff member are the same thing. But disjointedness would say things like, if I have party and I have a subtype of party called person and another subtype of party called company, I can define those as disjoint to say that they are not the same thing. In other words, a person is not a company and a company is not a person. And we can do further things for inferencing and reasoning. And taking it a bit further still, there are two more languages to be aware of, at least. There are many others, but we won't go into those that are widely used. There is a thing called SHACL, which is the shape constraint language. And the idea there is to define constraints on the schema of the graph, validation rules, and closed world checks. Something to realize is that the web ontology standards are open world assumption. In other words, there can be many things out there that if we don't have the data, we don't say it's invalid, we just don't know. Whereas in the typical database world, we have a closed world assumption where we say, well, we must know, otherwise we've got a problem. Okay. And if we do want to do those kind of validations, then SHACL allows us to express those. Then there's one more, which is CLIF, which is the common language interchange, common logic interchange format. And this allows us to express more detailed mathematical logic over related types and axioms that we want valid for our graph. Things like you might not have cycles occurring in the graph and things like that, and various ways of validating the graph. So a full ontology might be expressed in RDF, OWL, RDFS, CLIF, and SHACL together. So the structure is the data structure. We've defined the constraints. We may have added logic. So that kind of gives us enough now to make decisions. And if we can add agents where they can look at the graph, they can have this available information, they've got enough logic or rules to make decisions, then we can have automation at scale with reliable results. Yeah. So the model or models will find, generate, and filter information for us. Context can come from the ontology and the model, and we can provide information to the models as an ontology. That's often a knowledge graph and provided as retrieval augmented generation. So we can use the knowledge graph as the context to provide to the model. Obviously, we have harnesses that give us the user interaction like Claude or ChatGPT. They give us the ability to choose a suitable model underneath, to manage the models, to manage memory from session to session, and to get the right context, etc. Then agents can be triggered, and they can take action based upon information, the rules, and the outcomes. The ontology, given the schema plus the constraints, rules, derivation, inference, provides the additional meaning on top of the data that the LLM or AI is working with. The runtime system will often have a workflow, APIs to ERP and SaaS solutions underneath, and effectively this might be an enterprise scale harness that is working potentially with multiple LLMs, multiple contexts, multiple knowledge graphs, etc. Okay, so where do we find these ontologies? There's a whole lot of them. You can look for the basic formal ontology. There's UFO, which is the Unified Foundation Ontology, which is very popular in Europe, largely overlaps with BFO, but it does have some unique properties and constraints as well. Then there's CCO. There's a whole lot of derived ontologies from CCO. OBO is a foundry where you will find many ontologies in the life sciences world. There are also collections of ontologies defined at schema.org. And as of very recently, Ecosystem.ai is publishing a bunch of them at this domain catalog as well. If we have time, Jay may talk about that a little bit later. Okay, now when you go looking for these things, you'll find most of them will be in some sort of web ontology language or OWL format. OWL2 is the logical language in which the structure is expressed, and that gets serialized into various languages. So there are N-triples and there are various formats, XML and so forth. The primary language that is very popular is a thing called Turtle. And the idea behind that is it's a text version of OWL that is machine readable, but also human friendly. So it is easy enough to edit and work with, but it can also be machine processed. Another format is JSON LD, JSON linked data, which obviously uses JSON as the structuring and LD to provide the relationships and the other properties. SHACL, as we mentioned, gives you data validation and conformance. There are things like SCOS, which gives you standard taxonomies and vocabularies. RDF XML is another way of serializing RDF. CLIF is the common logic interchange format. And then there's also SPARQL, which is a query language, query and update, analogous to SQL in the relational world, but a bit more powerful. And SPARQL is often also used to validate ontologies by doing queries over them, or even to specify logic by doing updates on the concepts. Now, what's quite cool and what we've been doing for the last little while is to take these things. We may obviously have other schemas that we already work with, existing ERP systems, existing models that we work with in our industry, And now we want to exploit those together with AI. So how do we do that? What we're doing is merging things like XML schemas, OWL ontologies, information engineering, UML, entity relationship logical models, and re-engineered models from ERP and SaaS solutions, and then finding the common core meta concepts. And at this level, we're often going to use BFO and CCO concepts to anchor those. And then that allows us to start comparing the models, to merge them, to run integrated processes over the models. And we'll see the usefulness of that in a few moments. Okay, then to define the ontologies fully, we'll define our concepts and definitions. Those are often done in Turtle, as we mentioned. And maybe I can go out of present mode so we can show you what Turtle looks like. You'll see here you've got prefixes defined to say where is this definition living, and a lot of them live at W3.org, which is the World Wide Web Consortium. And then it's defining a real person as a class, and then it's saying a project is also a class, and it's a subclass of restriction. It has a property of a leader. This is a restriction being defined in OWL on the project class to say that the project leader must have a cardinality of 1. In other words, there must be a leader, and that leader must be a real person. Okay. So that's the kind of stuff we'll find in OWL. Now, there are also 2 graphical languages you can use for OWL. One is GOWL, graphical OWL, and the other is VOWL, visual OWL. They're both useful. GOWL maps all of the OWL concepts. VOWL maps less of them, but it's more concise, so it's easier to visualize a large ontology in. Okay. Then you may want to build specialization hierarchies, so the ISA or subtyping relationship, and you would think about also roles. So here you'll see, for example, we've said real person is a subtype of party, but customer is a role of party, and supplier is a role of party, and organization is a subtype of party, and organizations and real people are disjoint, and so on. Okay, so this is a GL model. All right, and then you also want to relate objects semantically, and you'll use containment, aggregation, composition, various other types of association. And generally, we want to name those in both directions. So I'll have something like this. An organization is the publisher of a reference. Reference is published by organization. Agent performs some kind of contribution, and so on. Okay. So this is a VL model, which is showing relationships between concepts in a reference ontology. Then we add properties, nothing too dramatic there. So you just specify names and you specify data types. Then we'll add constraints and rules. And as we said, that'll often use SHACL. So you might have data validation rules like this to say that this project code should be a string, and there's some pattern for it. So we wanted to start with PRJ, then have a numeric part, and so on. Okay. Then we might specify what kinds of objects we're expecting in places, like a project has a leader, which must be a real person. Cardinalities like this, we're expecting that the has-leader relationship will have a minimum of 1 and a maximum of 1. In other words, there must be exactly 1 leader. Then you can also specify things like requiredness. In other words, project name must be present. Disjointedness, like employee is not the same thing as external contractor. So you should never conflate those two because they're different rules that apply. And then derivation, something like this, where we're saying complete predicate type object completed project. Okay, so it's saying that if the status has a value of complete, then this project can move to a completed project type. Okay, right. Okay, then we would validate, and as I mentioned, there are, because we've now got something which is very well defined, we can actually run prover systems, apps, logic over the ontology, and there are a whole variety of provers available. And what they will do is test that the algorithms, the axioms that you've defined are actually being applied, and that the rules are not being broken in the lower level models. Okay. We would also want to check things like security, privacy, derivation and inference, and performance. Okay, we might need to iterate several times around the cycle, pull in stuff, merge, add, integrate, define, test, cycle back, and improve. When we finished, we'd want to publish, and there typically you're going to choose some standard outputs like Turtle to define your concepts, relationships, properties, and structure, and like SHACL to define constraints, and Cliff if you need to define any higher order logic. Okay, publish we've done. Okay, so how do we use these things? Well, you can use them to merge data sets. You can use them to integrate data models because we can equate the identifiers together. We can integrate across things like ERP, SaaS, and legacy systems. So we can see the concept and the relationship and where it occurs in underlying systems. And that allows us to automate workflows. We could also feed the ontology to a runtime platform as a shared context. So this is quite important. Instead of having a context per model at each instance, we can have a shared context, which then we draw from the relevant facts to provide to a model at a particular point. Okay, and this is starting to appear in large runtime platforms that the different industry players are starting to push. We'll see more on that. We can also feed the ontology to agentic engineering tools into an LLM, something like Ecosystem code or Claude code. We can give it a very structured model on which to base its generation of code. We can use it as a spec for more conventional development. We can use it as selection criteria for vendor solutions, and we could use it as a canonical reference model for integration. We can also use it in the same way that we traditionally used a domain model, and that is to look at the state of automation across our landscape, to look at ownership of who can make what changes across what concepts, where things are, redundancies and inconsistencies, which technologies we use, what archival requirements we have, what security requirements we have, etc. And obviously to drive logical and physical modeling, code generation, or runtime constraint validation. So an extremely useful thing once it's done. Okay, now what's happening in the industry? Obviously, everybody is trying to deploy AI, trying to scale it up, trying to get reliable results, and usually being disappointed. And then people have suddenly latched on to ontology as the golden solution and are saying, if we have ontology, then all of this problem goes away. And of course, there are some friendly vendors to help you do that. So we're trying to get to deterministic rather than probabilistic outcomes. Often we're providing LLMs with more context through things like vector databases, but we'd rather do RAG, retrieval, augmented generation. And the RAG, we would rather than use a vector database, we would rather use an ontology, which gives us much more structured, proven data. And the ontology can ground that decision making. So who's operating in this space? One of the earliest players is Palantir, who came into being to sort the mess out after 9/11, when the US government and military decided that they didn't actually know how to integrate the information that they were collecting. And Palantir developed techniques to do that and brought some very large systems and resources to bear on the problem. And they kind of led the industry in that space. Of course, there's Google. There's also Microsoft, and there are some of the players from the database, data warehouse world, Snowflake, Databricks, people like that, who've been doing data integration for a long time. The problem with all of these players currently is that they will help you to define your ontology, or they will provide a bunch of tools that allow you to define your ontology, but most of them are proprietary. In other words, the way that the ontology and the rules get expressed is particular to that supplier's platform. So you could spend upwards of $1.5 to $5 million with Palantir. They will come and, encode all your information into their ontology, all your rules into their logic language, and automate your business from end to end for a small fee. But you stuck. They now own your models, and you can't get out of there very easily at all. Okay, so how do we get away from that? Well, let's have a look at the platforms first before we go there. Here's an example from Palantir. You can see that they've got this ontology layer sitting in the middle, and they're saying that is their integration mechanism for how they bring in data sources and map them to one consistent view. It's also how they express logic in terms of what should happen and how decisions are taken. It's also how systems of action are identified and managed. So things like ERP and your source code management and your scheduling and everything is happening in there. And then on top of this, they're building your analytics and your workflows, your agentic automations, and your products and your development of your environment. So the ontology layer is really very, very central to what they're doing. Of course, our friendly Microsoft is also keen to get in on this act, and they've recently published their thing called Fabric IQ Ontology, and like many Microsoft and Oracle things, it runs best on a slide projector or a data projector. It's a great marketing model, and they say it sits in the middle, much like the Palantir one. It's going to find all the stuff in your physical environments and bring it all together and make it available for business intelligence, notebooks and data science, agentic workflows, and so on. The reality is a little more nuanced in the sense that underneath it, it's drawing on a lot of Microsoft data warehouse type products, and it assumes that all your data is sitting in Microsoft's lakehouse, which it may not be. And if it isn't, it has to be in there first before the stuff can run over it. So it's not quite as easy a picture as is being presented. Specifically, it has to live in one lake, which is kind of their cloud-based lake environment. So interesting. Some people will find it attractive if you're already heavily locked into, committed to the Microsoft world, but it may not be the best place to go if you are not there yet. Another honorable mention that I'll just bring in, it's not a major vendor, but it's one we came across and found quite impressive, is a company called Enterprise Web. And they've built an interesting model where they can go out and browse and scan APIs for all your existing ERPs and SaaS products. They discover the concepts from those systems. They map them into an ontology which they've built in their product, which is a graph domain model. And then they can catalog all the services available in the underlying systems. And then they provide LLM-based tools to allow you to compose workflows over them and then execute that in their runtime platform. So it's quite amazing. They can go out, interrogate the underlying systems, bring you all the components and services. You can engineer your workflow, and then you can execute an integrated transaction across all the underlying systems with things like transactionality, reversibility, and so on. And they've actually demonstrated that for some high-volume performance-critical systems. One we looked at was in the telecoms space, so actual telecom billing, which is non-trivial. Okay. So how do you avoid the lock-in? Bottom line is don't let the vendor do it for you. Don't let them force you into proprietary format. Do your own ontology so that you own it as your IP. Do that using standards, and the predominant ones are going to be OWL and Turtle and SHACL and Cliff. And do your own thing, own it. Then you can choose a platform to run it in, or you can choose to generate systems from it, or you can choose to, build parts of it through agentic AI, or however you want to do it. But own your own ontology is the bottom line. So what have we been doing at Inspired? I'm going to run through this fairly quickly, just to give you a sense of what we're doing on the periphery of this stuff. We've been building a thing called the Accessible Enterprise Ontology, or AON, and this is based on our previous work on the holistic architecture language. And the idea is to provide a generic enterprise ontology to underpin things like strategy, enterprise architecture, and agentic engineering. It's involved a group that's come into being across us in South Africa, collaborators in the USA, Canada, UK, Scotland, and India. And we've been able to include some pretty preeminent ontologists in that group. We've been running since about November last year, and we meet every week to try and progress the agenda. And we've examined and analyzed and merged and integrated a whole stack of ontologies, about 30 at last count that we've been looking through and figuring out. And along the way, we've also been evolving our tooling. Some of you may know our previous toolset, EVA. We're building a new generation of that graph-based, ontology-based, called Sapiento. So just to give you a quick flavor for some of these things, many of your organizations will use many of these sort of, quote, best-of-breed methods and techniques, BPMN and Archimate and UML and Agile and TOGAF. The problem is these things were often designed in isolation, and they have gaps, they have overlaps, they have conflicts, and they may also need context in which to operate. And it's kind of like a jigsaw where the pieces don't fit when you have to put it together. Okay, they're different sizes, different shapes, and they don't go together very nicely, so there's a lot of work to do. So what we've done over the years is taking some of the core enterprise architecture models like Archimate, TOGAF, etc., and many others. We built our integrated architecture language between 2014, 2019. Round about 2024, we added some more dimensions to it in terms of risk, maturity, assessment, and requirements. And in the last 2 years, we've been grounding that in formal ontology and doing better support for automated reasoning, including through agents. So the original HAL brought together many enterprise modeling approaches, EA frameworks, things used in strategy and business modeling and definition, and our historical meta models used in our tooling, also the risk framework and the maturity model stuff. So that gave us the holistic architecture language around about 2019 and evolving through 2022. 2, 3, somewhere there. That looks like this, where it addresses the context of the organization, the business issues, the process, the application, the information, the technology, and the change dimensions. And there's an overlay for security as well. And then just going into a little bit of detail underneath that, it maps all the concepts, the relationships to model those spaces in an EA or in a strategy type of context. Okay. The more recent work, we've taken HAL as a base, but then we've added the foundational and mid-level ontologies from various sources to ground this in industry standards and internationally accepted definitions. And we've also revised or, gone through to make sure we are looking at the latest versions of the other contributing frameworks. That's giving us an integrated model rooted in standard ontologies, and it covers generic concepts, context and boundary, business, enterprise risk, and change. Overall, we've got about 340 concepts and about 112 relationship types. Okay. So now the pieces fit. We get a jigsaw where the bits are made properly, and we can put the pieces together and start using them together, and the picture is quite pretty. Okay, we've also been building our tooling, and I've got about 2 more slides to do, and then we'll be wrapping up. So what we've been doing is building this tooling called Sapiento, which is an EVA successor. It's graph-based, it's repository-based, it does both modeling and execution. We can take in IE, UML, ER style models, RDF, turtle models, XML, SHACL, and Cliff. We can output turtle. We can do query and updating through Cypher, which is a graph language, or GraphQL. And you can model in text or graphical form. So here you see, for example, OWL, from which we've generated a GL model, and we can work in the model and generate the code back again, or do it either way around. Okay. But importantly, the model is the runtime. So the tooling adapts the moment you define the model. You can also navigate over it, capture instances, report over it, etc., etc. I don't want to spend long on it, but there are many capabilities. It's multi-level, so it works both on meta and instances. And you can model, browse, edit, analyze meta and instance. Many different ways of looking at the data as a tree instance inspector view, reporting, matrices, tables. You can walk the semantic graph either conceptually or instances. You can do models, you can do authoring. The notations are also extensible, so we can do GL, we can do Archimate, we can do entity relationship, etc. And we can do some visualization, some query and updating in Cypher or XML or GraphQL. And we can import, align, merge, and export ontologies at a namespace level. So that's what we've been doing. And I'd encourage you to stay in touch if you want to know more, and happy to chat or answer questions at this point.
Do we have any questions? If we do have any questions, please, and you haven't been made a contributor yet, please feel free to raise your hand, or if you prefer, you can drop it in the chat.
I've got maybe just a comment for everybody. I think that the agentic reliability, and what we probably can do at some future session, is just to show the mapping of the SHACL and OWL and the turtle files to real data assets inside the organization, so that when they use your framework, I think that taking that output and putting it into a tool like Ecosystem Code, or wanting to understand how you're going to deploy a reliable deterministic system, that you have a definition that the business agrees to. because I think that you did make the point, but I think maybe just to repeat that, is that we're seeing so many projects where people are working on system migrations, and by the time they deal with mapping of data and trying to understand where all the changes are that are required, and they then do it, specific to this one vendor. If you think of, like, we've been dealing with clients trying to understand how they get, let's say, Salesforce implemented. You spend 5 years trying to get it working, and 80% of your effort is just doing mapping and hacking away until you get it to work, rather than taking the exact way in which you conduct your business and then use AI to evolve at the pace that the business needs to evolve. So I think there's kind of a new mindset developing that that this enables beyond, I think, what people might perceive as being valuable initially. We see now with some conversations with clients that there are the questions, so why do I need this? And it's only when they really are in the heart of a transformation project that they just see, well, hang on, I don't understand any of these things really. I rely on some technical implementation, somebody that's, denormalized a table, created technical keys, created rules that are different across different systems, hacked into the front end some rules that make one, data value change in one place but not another. There's just this kind of large mess of interrelationships that this attempts to solve.
Yeah, totally agree. Okay.
Then, I think we must definitely look at setting that up as another session later down the line. I know we've got a lot more discussions on ontologies coming up.
I can recommend something, Maddie. What we do, we take one of Graham's exports, a SHACL that he creates, or an OWL, and we generate the system in code, ecosystem code, and we then discuss the complexities of that migration.
Sounds good.
And then that's one thing. And then at the same time, we can then take, if you look at the ecogentic platform and ecosystem, if you guide an ecogentic journey with an ontology, the inherent rules and decisions simplify your journey enormously. And you focus on the business value of the flow rather than worrying about all the conditions that you have to define. So we can take kind of like a two-prong approach and make it a technical session. So I think people might enjoy that.
Sure, I think that sounds good.
Yeah, I think another take on that, Jay, that's kind of a forward engineering one. I think another one that's quite important, which might be an interesting one, is you've got a couple of existing runtime systems, maybe one ERP and one SaaS environment, and you need to run a business process over the top of those. So how do you actually get the common model, and then how do you write the logic for the common, or to run over the top of the existing systems?
Yeah, no, that's a good point, because I know that we've been working on, you can connect to a SQL database or a Mongo, so SQL or NoSQL, reverse engineer the data model into the designer, and then write out the ontology. The problem is that it sounds easy and practical, but in the real world, it has got enormous implications. So that's why you need something like what you're working on, Graham, where people still need to then think about the re-architecting. There's no point replicating all of the challenges that you had in the previous architectural cycle or the previous technological deployment verbatim into your new deployment. So that's why there's this round tripping, reverse and forward engineering both present interesting challenges that always sound easier than they really are.
Yeah, for sure. Okay. Okay.
On that note, are there any closing questions?
May I just add a little comment?
Sure.
Go for it.
Yeah, so very interesting. Thank you so much. It kept me awake. No, really, really interesting. Look, I'm working deep in a startup in the SQL domain. I know SQL is old hat, but what we find is, for example, you mentioned Databricks, Snowflake. If you look around the whole data infrastructure, you see multiple table formats, multiple catalog formats, Parquet, Iceberg, and Delta in particular. But one of the big problems is that if you're running an SQL query, you really butt up against the fact that you cannot be agnostic to these formats. You mentioned it yourself with the fact that for Palantir, for example, has a proprietary catalog format. That's essentially what you're talking about. And so what we're doing is I'm part of the team. It's not my only work, but I'm part of the team that is essentially, if I can put it this way, agnostifying the SQL query manufacture. So we run extensive queries through a column-based implementation, rather like ClickHouse, rather than a row-based. So it's extremely fast. And then the queries are then, through obviously the Terminator, the workers. It's all in the cloud, of course. And then it has its own agnostic catalog, which is essentially any format in, any format out, without any data logging other than the minimal amount ephemerally needed to process the articles, right? The queries. Of course, it's multi-tenant, etc. So what I see, is you could have a SHACL property dump into. It's called Flow, by the way. I'm not trying to sell the platform. It's all anyway. It's only in beta. But if you're interested, it's Flow FLOE. And a very small, exciting team. And you can go have a look. It's in Git as well. We're trying to make this open source. So you could have a SHACL property, dump into a flow-based SQL table column, have an extraction query that comes out agnostic, and then go into an RDF, and then back into a SHACL result. And so you could build your SQL, for example, a compliance finding, right? Very, very quickly synthesizing SHACL and what we think we have in extremely fast, agnostic, ubiquitous SQL without having to go through the proprietary gates. I'll leave it at that, but I'd love to carry on this. Very, very exciting. Thank you.
Are you guys building it in your current consulting business, or you external?
No, this is so my consulting, I was hired by Neil Carson, who is the CEO of Flow. You can go and have a look at Flow. It has a website.
But you're still working with God and everybody, right?
Oh yeah, absolutely. And I'm the CISO, a fractional CISO for Flow, essentially, right?
Okay.
Yeah.
Okay.
And it's
how we'll have a look. That's interesting. Like it.
Yeah, it's really, really interesting, and I know the team would be really open to anybody coming in and wanting to experiment, and I encourage you to and give feedback. It probably isn't particularly amenable right now because the team is still building. It's in beta, but I'd love to have that dialogue with anyone on this call that's interested. So just reach out to me, please do.
Maybe if you could go. Maybe just have a look at this. I'll share the repo that we've made public.
Oh, excellent. Yeah.
It's got 39 business domains, and the reason why we created it is to assist business people with a generic definition where most of the definitions there were reverse engineered from and created from current major enterprise platforms.
Okay,
so the thing is that if you have a look at,
I
like
put it on
CRM,
screen for you, Jay.
Yep, I've got it. It's okay. Yeah.
Yes, and you'll see that there's an area called mappings, and inside mappings there's a SQL mapping.
Interesting.
And there are purely examples in the public repo. But if Flow can assist, let's say a company wants to take their 5 CRM systems and produce a single one, and they want to generate out a deterministic system using ecosystem code, we need data mapping done, otherwise nothing works.
Right, absolutely.
So Graham's world, the company would model it, because you need to model what you're going to be doing, and there's just too many complex moving parts to do it, kind of haphazardly. And then by the time you look at the technical pieces to construct it, and you want to bring the old data in, you need that mapping done. So we've created a mapping between OWL and Turtle and some SQL examples. That's why they say samples. They're not. We have been testing some of them, but there are quite a lot of obstacles still in that space. So yeah, we definitely would be willing to chat about how we deal with that.
Yeah, I mean, the whole driver here is I see a real powerful synthesis between SHACL and what I'm going to call naked SQL, if I can. No PG, no PG stuff, no proprietary data delta. No, it's purely naked SQL, if you like, and make it as fast and as amenable and as available as possible to any entity that wants to just run powerful SQL. And SQL is still, the baseline for all of these databases anyway.
Yeah, I think we've got to be able to merge data from many different physical models these days, because you've got the traditional SQL world, which, as you say, is the bulk of commercial stuff. But there's also document, there's also graph, there's also semantic, there's also XML, there's JSON LD, there's 56 data formats, and you need actually to be able to bring them together, and the answer is a semantic layer.
Correct.
And I mean, Sapiento is still very young, but what we're already doing is we can bring in, in XML, we can bring in plant, we can bring in SHACL, we can bring in OWL, and it all goes into a semantic model, which is grounded at the top in the same core concepts. So we can bring those in, compare them logically, and see what's in both, merge them if we want to, and then export them in other formats. So basically it's whatever format in, semantic inside, and whatever format out kind of thing. Now, we're not trying to do it at volume, at scale, at massive performance, which is where you guys are going to play. But for modeling and for deciding how you want to do this, that's the space we're playing in.
I mean, that'll be what, if you do the technical session, if you're interested, we can maybe just do a pre-briefing, see what the tooling looks like, and we can do a session here on one of our Wednesday years. Because I think that for us, even if you go to the developer.ecosystem.ai and the like, we've now published our behavioral science products ontology. We've published, all of them are available, so it makes it easy for companies to integrate and use it. So whichever tooling assists with that, and especially the visualization at an enterprise level, like what Graham's doing, helps people to understand the broader picture. But at the end of the day, our world is heavily rooted in the physical estate and the physical data connection at volume, that needs to work on the ground. We need to bring all layers together. So it's great. That's it from me. Thanks.
Yeah, me too. It's very exciting. Thank you. Really, really, really interesting.
Thanks.
Okay.
Thank you, everyone. I look forward to the future discussions. I think it'll be, a good few sessions coming up. With that said, I think we can call it. And I'm going to say happy Wednesday to everyone and have a good evening.
Okay.
Thanks,
cool.
Brandon.
Thank you. Take care.
Thanks, everyone. Cheers. Bye.
Bye now.